Hi everybody. We're going to be doing section 2.4, which is called Row-Echelon Matrices and elementary row operations. So, what we're going to be learning is a strategy for solving a system of equations using matrices. So let's first talk about the strategy for solving a system that we are very familiar with previously. So, what is back substitution? Let me give an example of a matrix using back substitution. So, an example, x1 plus x2 plus x3 is equal to 6. x2 minus 4x3 is equal to negative 4. And x3 is equal to 3. Obviously, this system is much simpler than a normal system because of the way that it's structured here. But I want us to see something here. We already know what x3 is, right? And so what we could do is take x3, which is right here, and substitute it in for x3 right here. Okay, so if we do that, we get x2 minus 4 times 3 is equal to negative 4, or x2 minus 12 is equal to negative 4, or x2 is equal to 8, right? So we just substituted it back in, and now we can take this guy and substitute it in for x2, and of course we can still substitute x3 in, and so we get x1 plus 8 plus 3 is equal to 6, or x1 plus 11 is equal to 6, which means that x1 is equal to negative 5. And so our solution to the system is negative 5, 8, 3. Okay. Now, looking at this system, of course, you may be wondering, well, what do I do if the system doesn't look all nice like this, right? Obviously, there's usually more work to do. So we'll get to that in a moment, but I want to show you guys exactly what the augmented system looks like here. We have a 1, a 1, a 1, and a 6. Then we have a 0, a 1, and a negative 4, and a negative 4. And then we have a 0, a 0, a 1, and a 3, right? Notice that we have 1s all along the diagonal here and 0s underneath it. This has a name. This matrix is in row-echelon form. Okay, so I want us to define that in the next slide. So definition. An M by N matrix is a row-echelon matrix if it satisfies the following conditions. first condition if there are any rows consisting entirely of zeros, they are grouped at the bottom of the matrix. Second condition, the first non-zero element of every row is a 1. And 3, the leading one of any row below the first row is to the right of the leading one above it. So these are the 3 conditions. All 3 of these conditions must be met, and if they are, then a matrix is called row echelon. So if we go back to this last example, this was a row echelon matrix, right? Because, let's look. First, each row starts with a 1. Also, each row after the first one has a 1. The leading one is to the right of the leading one above it. And finally, there are no rows consisting of zeros. If there were, they would need to be at the bottom, but there aren't any, so we're good on that first condition. Okay, so this meets all 3 conditions, so it is a row echelon matrix. So as an example, I would like for us to practice identifying if matrices are row echelon. We need to be able to do that. So, are the following matrices row echelon? First matrix, 1, 0, 0, negative 8, 1, 0, negative 3, 5, 0, 7, 9, 1. Is this matrix row echelon? The answer is yes, right? It meets all 3 conditions. Okay, all of the leading numbers on each row that aren't zeros is a 1. All the ones occur to the right of the one of the rows above it, and there are no non-zero rows in this one, so we're good there. Okay, let's look at the next one. Is this row echelon? The answer is no. Why not? Because there's a row of zeros that is not entirely at the bottom. Okay, so that row needs to be at the bottom in order for this to be row echelon. Okay, so the answer is no. Okay, let's do another one. would this be considered row echelon? The answer is no. Why? Because the second row doesn't have a leading 1. It has a leading 2, doesn't it? So because of this guy right here, the answer is no. Okay. Let's try another one. How about this matrix? Let's check. Are all the rows with all zeros at the bottom? Yes. We've got the first row has a 1 as its first non-zero digit. Yes. And then we don't have any more leading 1s, so the answer is yes. This is row echelon. Meets all 3 conditions. I have a couple more that I want to do. I'm just trying to illustrate all the different examples so that you guys have an idea here, okay? So let's look at the next one here. This will be part E. One, zero, 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 negative 3, 0, 0, 0. Negative 6, 1, 0, 0, 5, 3, 1, 0, 4, negative 8, 0, 0. Is this row echelon? Well, let's see. We have our row of zeros is all the way at the bottom, which is good. And we have leading 1 at the top. The second leading 1 is to the right. The third leading 1 is to the right. So the answer is yes, it is row echelon. Okay, we're going to do one more here. How about this? 1, 0, 0, 0, 1, 1, negative 1, 2, negative 1. What's the problem here? The problem with this one is this one right here. That should not be there, right? Because all the leading ones have to be to the right of the leading 1 in the row above it. And so the answer to this would be no. So that's the end of that example. I hope that that clarifies what it means for a matrix to be in row echelon form. Okay. So let's go ahead and write down one little thing before I talk about something a little different, okay? So as our new form of conversation here, just because a matrix is not in row echelon, it doesn't mean that we cannot do stuff to it in order to turn it into a row echelon matrix. So let's talk about that. There are operations we can do to any system coefficient matrix to change it into a row echelon matrix without changing the solution set of the system. This is really, really important, okay? This means, things that we do to equations are not useful if they change the solutions of the equation. What we're interested in is how can we make things easier to work with and find answers to things without contaminating the solution set. And so we have operations called elementary row operations, And that's what we're going to discuss right now. So here are the three things that we are allowed to do. The first thing we're allowed to do is permute rows. Permute rows. What does permute mean? It means to switch two rows of a matrix. We are allowed to do that anytime we want, and it does not change the solution set. Okay, so what is the notation? It's Pij. This just means permute rows I and j. So this means that row I and row j get switched. Second, row operation. We are allowed to multiply any row by a non-zero constant. Let's call it k. Multiply any row by a non-zero constant. Actually, let me not give it a letter here. So the way that we would write this out is we would write it like this. We would write it like with a capital M, okay? So a capital M sub I of k, this means to multiply row I by k. Multiply the ith row by k. So that means that k times row I becomes the new row I. Finally, this is probably the most useful one. We are allowed to add a multiple of a row to another row. So the way we do that is with a capital A. Capital A. So if you see capital A and then IJ and then you have a K, the way you read this is you take K times row I is added to row J. Again, so that means K row I plus row J becomes the new row J. All right, everybody, so these are the notations that you must learn. I'm going to highlight them here. This guy, and this guy, okay? So if you see a P, it means permute. If you see an M, it means multiply the row. And if you see an A, it means you're going to add a multiple of a row to another row. Okay, so just a little bit of notation here. We need to learn what it means to have a little squiggly line here, that actually means the word row equivalent. So A is row equivalent to B. So what this means B can be obtained from A using elementary row operations. So the way you say that again is A is row equivalent to B. And most importantly is a theorem. The theorem says every matrix is row equivalent to a row echelon matrix. Okay, so I would like to teach you guys how to put a matrix in row echelon form. This is going to be an extremely important skill that we use throughout this class. So let's do some examples. Our first example. Reduce to row echelon. So here's our matrix. 2, 1, negative 4, 2, 1, negative 1, 6, 0, negative 1, 2, negative 7, 1, and 3, 1, 1, 3. So before I do the problem, I just want to give you guys sort of our goal or our strategy here. Our strategy is to work from the upper left corner to the bottom right corner. You basically work to get that 1 there, and then you try to get everything below it to be a 0, and that's how it goes. Okay, so let me show you how this works. So let's start with getting a 1 in the upper left corner if possible, which we can do here. What is the easiest way to do this? And there are a couple of ways of doing this, but we want to avoid using fractions. So let me just show you. A naive way to do this might be to just take the first row and multiply it by a half. And yes, that would give us a 1 in the upper left corner, but then what it would do is it would give fractions for all the rest of the guys in row 1, and we want to avoid using fractions if possible. Now, of course, towards the end, we're not going to be able to avoid fractions, but we want to avoid them as long as possible because it gives us less room for error. So what's an easier way to get a 1 up there? We could just switch or permute rows 1 and 2. So I'm going to write P1, 2. And that just means switch row 1 and 2. And so we're left with 1, negative 1, 2, 1, 2, 1, negative 1, 3, negative 4, 6, negative 7, 1, 2, 0, 1, 3. Okay. Now what? Now we want to take all 3 of these guys. I'm going to highlight them. All 3 of these guys right here and turn them into a 0. The way we could do that, once you have a 1 up there, is we can add multiples of that guy to the other guys. So we're going to use our A notation or our A operation. So here's how it works. First thing we can do is we can add negative 2 times row 1 and add it to row 2. negative 2 times row 1 and add it to row 2, right? Why is that? Because negative 2 times 1 is negative 2, and if you add it to 2, you get 0. And so before I do the other operations, I just want to show you what we're going to get here, okay? So row 1, we're going to leave alone. So 1, negative 1, 2, and 1. But now row 2, after we do that operation, is going to become, let's see, negative 2 times 1 plus 2 is 0. Negative 2 times negative 1 is 2 plus 1 is 3. Negative 2 times 2 is negative 4. Minus 1 is negative 5. And negative 2 times 1 is negative 2, plus 3 is 1. You notice that we got our 0 there? We're going to do that for the other ones also. So here we're going to add 4 times row 1 and add it to row 3. And then we're also going to take negative 2, row 1, and add it to row 4. So all of that gets done here. Let me put my little squiggly. You know what? I'll put the squiggly here. In other words, I'm trying to say that all of these are connected, okay? And so I end up with 0, 2, 1, 5. And then I get a 0, 2, negative 3, and 1. The point is, we got all of those to be zeros. So now what's our next goal? Our next goal, we're done with the first row and the first column, so now we move to this guy. I'm going to circle it. We move to this guy. So our next goal is going to be to turn that guy into a 1. Now, sadly, there is no nice little switch way we could do this. So the only thing we can do is multiply that row by 1/3, which is going to give us some fractions, but there's nothing we can really do about that. So we're multiplying row 2 by 1/3. So all the rest are going to stay the same. So 1, negative 1, 2, 1. 0, remember we're multiplying this row by 1/3, so we get 0, 1, negative 5/3, and 1/3. And then the rest stay the same, so 0, 2, 1, 5, and 0, 2, negative 3, 1. Now what? Now that we have a 1, we need to get rid of these guys, right? We want to turn those guys into a 0 using the 1 above it, okay? So I'm going to add negative 2 times row 2 added to row 3. And I'm also going to add negative 2 times row 2 added to row 4, right? That's how you can get a 1 to cancel out a 2, right? Because the 1's going to become a negative 2. Added to 2, we get 0. So let's write down the first 2 rows. Those are not going to change. So if we add a negative 2 times 1 added to 2, of course we get 0. Negative 2 times negative 5/3 is 10/3. 10/3 added to 1 is 13/3, right? 13/3. And negative 2 times 1/3 is negative 2/3. Negative 2/3 added to 5. That's negative 2/3 added to 15/3 is 13/3 again. Okay, what about the last one? I've already worked this one out. It's 0, 0, 1/3, and 1/3. Okay, so we're done with those two. Now we need to work on this guy. we need to turn that guy into a 1. So we're going to multiply row 3 by 3 over 13. Sorry, it should be like this. Multiply row 3 by 3 over 13. By the way, yeah, so let's just go ahead and do that, okay? So if we do that, we end up with, so the first two rows are going to stay the same. 1, -1, 2, 1, 0, 1, -5/3, 1/3, 0, 0. Remember, we're multiplying it by 3 over 13. That gives us a 1. If you multiply the next one by 3 over 13, we also get a 1. And then the last guy stays the same. 0, 0, 1/3, and 1/3. Okay, now what? Now we need to deal with this guy right here. We want to turn that guy into a 0. How do we do that? We can add a multiple of the guy above it to that. So how do we do that? We want to add -1/3 times row 3 added to row 4. So let me go ahead and actually copy, yeah. So let me write that down here. We're going to add -1/3 row 3 to what row 4. We're going to add -1/3 row 3 to row 4. So let's go ahead and write down what we had before. We had 1, -1, 2, 1, 0, 1, -5/3, 1/3. And then we had 0, 0, 1, 1. And now what? -1/3 plus 1/3, of course, is 0. And then we have -1/3 times 1 added to 1/3 also gives us a 0, right? So actually we get 2 zeros at the bottom. So we are done. Why are we done? Because we have a leading 1 in each row. It's always to the right of the one above it, and all of our full 0 rows are at the bottom, so we are finished. This would be our answer. This is our row echelon form of the matrix. Okay, I hope that was clear. I would like for us to do one more example here. Or one more example of this, I should say. We are going to do a little bit more. Okay. So again, I want us to reduce to row echelon. So we have 3, 1, 1, 2, 1, 0, -5, -1, 3, 2, 1, 4. So what could we do first? Well, to get a 1 in the upper left corner, we could just do something easy, which is to swap row 1 and row 2, right? Just like last time. So we're going to permute row 1 and row 2. So if we do that, we end up with 1, 1, -1, 1. Then we get 3, 2, -5, 2. And the last row stays the same. Okay. Now what? Now we're going to add, right? We want to get rid of these, don't we? We want to turn these into a 0. So we do that by adding row 1 to the other rows. So I'm going to add -3 row 1s to row 2. We're also going to add -1 row 1s to row 3. Okay. So we get 1, 1, negative 1, 1. And then we get 0, negative 1, negative 2, negative 1. And then we get 0, negative 1, negative 2, and negative 3. So we've got our zeros there. Now we need to turn that guy into a 1. There's an easy way to do that. Just multiply it by, of course, it's reciprocal, which is just the same as multiplying it by negative 1, right? So we're going to multiply row 2 by negative 1. Multiply row 2 by negative 1. So everything else stays the same, so let's write that down. 0, 1, 2, 1, and then the bottom stays the same. Now what? Now we need to turn this guy right here into a 0. We do that by using row 2. But in this case, we could just add 1 of row 1 to, or sorry, of row 2 to row 3. So we're going to add 1 times row 2 added to row 3. So we get 1, 1, negative 1, 1, 0, 1, 2, 1. And then here we get 0. We're basically just adding the two rows together. 0 and negative 2. So this is what we get. Okay. Actually, I think negative 1 times row 1 added to row 3. Sorry, I have a typo here. This up here should have been a positive 3. So positive 3. So yes, I did make a mistake here. I just noticed it. And so when you add row 2 to row 3, we actually get a 4 at the bottom. So I apologize. I had a sign error on earlier step. So there we go. We fixed it. Now that we're here, the last step will be to turn that last 4 into a 1, right? We want to turn this guy right here into a 1. And so we can just multiply row 3 by, multiply row 3 by a 4th. And we get 1, 1, negative 1, 1, 0, 1, 2, 1, and 0, 0, 0, 1. There we go. We've got our row echelon there. Let's put a little box around that guy. Okay, so let's give a couple of extra results and one more definition here before we're done with this section. So let's go ahead and give a theorem first. First theorem. All row equivalent row echelon matrices have the same number of non-zero rows. Okay, so before maybe I should have said this before I wrote down the theorem. So something we should note. If we go back here, note, row echelon matrices are not unique. What do I mean by that? What I mean by that is it's possible that if you had done this problem using a different order of things, and maybe what you could have done is started with switching row 1 and row 3. instead of row 1 and row 2. That would still have put a 1 up there, right? So your answer at the end would look different than my answer. Your answer would not be the same matrix as my answer, and that's okay. There's not a unique answer here. However, there is something that they have in common, and that's what the next theorem says, which is all row-equivalent row-echelon matrices have the same number of non-zero rows. Same number of non-zero rows. Okay, so let's look at this last problem. This last problem had 3 non-zero rows. That's unique. In other words, no matter which method you use to do that problem, you would have ended up with a matrix at the end that has no non-zero rows. That would have matched. Or that has, sorry, yeah. That has 3 non-zero rows, I mean. Okay. So, because all row-equivalent row-echelon matrices have the same number of non-zero rows, we give that number a name. So, definition. The rank of a matrix A denoted rank of A is the number of non-zero rows of the row echelon form of A. Okay. So if we go back to our last example, let's say that we were to call this matrix that we started off with A. Then we can go ahead and write down the rank of A. The rank of A is 3, right? Because we ended up with an answer that had 3 non-zero rows. So the rank is 3. Okay, so that is our definition. And let's write down an interesting fact about this. We are limited in what the rank can be, right? So fact, if A is an m by n matrix, then the rank of A, of course, you're limited by how many rows there are, right? The rank of A is smaller or equal, so less than or equal to m. However, what else must be true? Notice that you can only have as many leading ones as there are columns of the matrix, right? If there's less columns than rows, then you're going to have a non-zero row. So also, the rank of A has to be less than or equal to n as well. So this means that the rank of A is less than or equal to whatever the minimum is of m and n. So we have an upper bound now for what the rank of a matrix can be. It's the minimum of the number of rows and columns that the matrix has. Okay? Okay, so we have one more definition to give. A matrix A is, what does it mean to be a reduced row echelon matrix? Reduced row echelon matrix. So this has two conditions. First of all, It is row echelon. Okay, so of course, any reduced row echelon has to be row echelon. And this second condition is the one that is important. Any column that contains a leading one has zeros everywhere else. So any column that contains a leading one has zeros everywhere else. So, as an example, the following are all reduced row echelon matrices. So let's write down some examples. 1, 0, 0, 3, 0, 0, 0, 1, 0, 0, 0, 1. That's a reduced row echelon because every row with a leading 1 has zeros everywhere else. I'll highlight them. Look, right there, and right there. You notice wherever you have a 1, you have zeros everywhere else. Notice you don't need to have that for row echelon. You only needed zeros below the 1s. You didn't need it above before. Okay, what about this one? 1, 0, -1, 0, -1, 0, 0, 1. Yes, that is row echelon, of course, because of those and those, right? Those are the only two, so those are the leading ones, and those columns have zeros everywhere else. How about this one? 1, 0, 0, 0, 1, 0, 5, 2, 0, 3, 1, 0. So yes, this one is row echelon because of that and because of that, right? Because those are the only two leading ones. The third row is a 0 row, so that has no leading ones, of course. One, 0, 0, 0, 1, 0, 0, 0, 1. Of course, here, all three columns have leading ones in them, and they all have zeros everywhere else. Now, you might have a question. You remember before we said that row echelon forms are not unique, but what about reduced row echelon forms? Are those at least unique? So the answer is yes. So this is our theorem here. That means any strategy that you use is going to produce the same answer at the end. Every pair of row equivalent reduced row echelon matrices are equal. I actually, earlier on when I wrote something, I need to be careful here. I think I missed the word. I should say row reduced. In other words, only if they all come from if they all come from a row reduced form of the same matrix, right? But here what we're saying is that it is unique. They are all equal to each other. Okay, so let's do an example. So of a reduced row echelon form. Now, reduced row echelon is a lot more work than the other because there's more zeros that we have to put there, but it's not that bad. We just have to get used to it. 2, 1, negative 4, 2, 1, negative 1, 6, 0, negative 1, 2, negative 7, and 1, and 3, 1, 1, 3. So this is our starting matrix. So we're going to begin this. And if you notice that this is actually an old example that we did, right? A couple of examples ago, we did this problem. 2, 1, yeah. So we did this a couple of examples ago. And so maybe what we could do is we could at least start with our answer that we got last time. Maybe not start with our answer that we got last time. Well, yeah, let's do that. Okay, so let me just say by old example, we already did the work and we got that this is equal to, or row equivalent to the following: 1, 0, 0, 0, negative 1, 1, 0, 0, 2, negative 5/3, 1, 0, and 1, 1/3, 1, 0. So the only difference is when you're doing these problems and you want to get reduced row echelon, you just need to use, as soon as you get a 1, you can use it to get rid of the zeros or get rid of the numbers below and above it. So in other words, we're going to start by using this 1 right here to get rid of this guy above it, right? We want to turn that guy above it into a 0. So we can do that by adding row 2 to row 1. So we're going to add 1 times row 2 added to row 1. Okay? So what do we get? We get 1, 0, right? Because that's a 0. If we add negative 5/3 to 2, so that's negative 5/3 to 6/3, we end up with 1/3. And then if we add 1/3 to 1, we get 4/3. Everything else is going to stay the same. There we go. So we're done with column 2. Now we got to work on column 3. We need to use this one right here to get rid of these two guys above it, right? We got to turn those into zeros. So how do we do that? Same as before, we just add multiples of that 1 to the ones above it, right? So we're going to add negative 1/3 row 3 to row 1. And we're going to add 5/3 row 3 to row 2. What do we end up with? We end up with, so this is going to become a 0. And I'm sorry, that was already a 0. We're adding negative 1/3 row 3 to row 1, so that's a 0. And then negative 1/3 times 1 is negative 1/3 plus 4/3 is a 1. So we get a 1 there. And what about this next guy? This is a 0, that's a 1. So 5/3 times 1 plus negative 5/3 is a 0. And then 5/3 times 1 is 5/3 plus 1/3 is a 2. Third row stays the same. And then the last row also stays the same. Notice we are done, right? Because we have all zeros, all zeros, all zeros in those leading 1 columns. So we're good to go. This is our answer. Okay, so we don't work with reduced row echelon that often. Sometimes we're going to work with those. I just wanted to let you know that this is a thing that does exist, and we're going to see that we can solve problems in the future using reduced row echelon, but normally row echelon is good enough. It's a lot less work, and it gets us to the answer relatively quickly. All right, everybody, that's it for this video for 2.4. Thank you so much for watching.